We are starting Chapter 3, Section 6, One-to-One Functions and Inverse Functions. Okay. Let's see. Okay. So real quickly, before we begin this, let's just try to dive into what we mean by functions and all that stuff, right? Because I know that we hear functions, one-to-one functions, and inverse functions, that they all start to jumble up, and then we're like, well, what is which? Okay. Well, first of all, we're going to start with we're just gonna have like a little, not necessarily a flow chart, but kind of a hierarchy. Okay. We're going to start with the equation. Okay. Golly, that doesn't look like equation at all, does it? I actually have good handwriting. It's just this tablet makes things a little weird. Okay, so we have the equation. In anything in math, anything in math is an equation. Okay, and so that's kind of like the superset. Okay, and then a subset of that, okay, we're going to call the function. Okay, and so a function is an equation, but it's a specific type. It's a specific type of equation. Okay. We know that functions, for every 1x, there's, well, hang on, yeah, for every 1x, there's exactly 1y, right? That is an example of what a function is. We know equations, can be, the circle equation. All right, we know the circle equation, violates the vertical line test, right? But, that's an equation, that's fine, it's nothing wrong with that, right? But a function, again, must pass a vertical line test, and that's simply a function. Okay. All right. Well, a subset of a function will be a one-to-one function. Okay. And then a subset of that will be an inverse function. And inverse, whatever. There it is. Okay. So a function is an equation. Okay, a one-to-one function is a function, and an inverse function is a one-to-one function, which is a function. I know it gets kind of complicated, and I might not have done you guys any favors there, but I tried. Actually, I'm going to go ahead and snip this and talk about this. I don't think it's. I think it's good, actually. Yeah, I was going to say I don't think it's too terrible, but I think it's good. All right. So from the top, in this section we study inverse functions. To illustrate an inverse function, let's consider the function f of c is equal to 9 over 5 c plus 32. You might recognize this as the function to convert Celsius to Fahrenheit. Okay, that's where it says. Yeah, this function is used to convert a given temperature in degrees Celsius into its equivalent temperature in degrees Fahrenheit. And then, of course, if you have 25 degrees Celsius, you plug 25 into there, and you get 77 degrees Fahrenheit. Right. Thus, a temperature of 25 degrees Celsius, okay. And then the function that is used to accomplish the task going from Fahrenheit to Celsius is this function right here. Okay. So these two functions, this function and this function, are inverses of one another. Whenever you put an output from one function and input it into another function, you get the output of the original function. That's confusing also, but let's see if better words can be used. All right, so the function c is the inverse of the function f. In essence, these functions perform opposite actions. They undo one another. The first function converts 25 degrees Celsius into 77 degrees Fahrenheit, whereas the second function converted 77 degrees Fahrenheit back to 25 degrees Celsius. Okay, and I guess that that's again, I say better words. These are definitely pretty good words to use. Yes, they undo one another. Right. And here we're going to have our definitions. Alright, so first we must define the concept of a one-to-one function. So let's see, is this definition any good? A function f is one-to-one if for any value a not equal to b, okay, so if a is not equal to b in the domain of f, then f of a is not equal to f of b, okay, so let me break that down for you real quickly. Okay, for any values a not equal to b. Okay, now this can just be, you know, 2 is not equal to 3. Easy peasy. Okay, we can agree that 2 is not equal to 3. So as long as the excuse me, so as long as the x's do not equal to one another, then their y's should not equal to one another either. So a one-to-one function, it means that exactly one x is going to go to exactly one y. Okay, so in the past when we talked about a function, all right, so let's see if I can put this over here. Okay, so in the past when we talked about a function, one x value can go to only one y. Okay, it doesn't matter what x it is. Okay, it can only go to one y value, and that's perfectly fine, right? An example of what I just drew here would simply just be the horizontal line, right? All these values of x's are exactly equal to this, you know, whatever that's located at. You know, if I want to give some raw numbers here, you know, this was maybe like a 2, right? So at 2. So all the x values, you know, negative 2, negative 1, 1, and 2, they're all equal to 2, that horizontal line there at y. Okay, that's okay though, because that is a function. That is indeed a function. It passes that vertical line test. Okay, well now a one-to-one function goes just a little bit further, and it does exactly what it sounds like, or it is exactly what it sounds like, right? It is a one-to-one function, right? So only one x goes to one y. So for instance, this is not a one-to-one function because the y value right here at 2 is being used for every single x value. That is not allowed for a one-to-one function. So I'm actually okay with the original definition here. We'll also look at the alternate definition because it might help out a little bit better. But if you just break this down and you know the way I just did, you'll get a better understanding. But realistically, again, in cornbread language, one x, one y, period. Okay. So here we go. This definition suggests that a function is one-to-one if for any two different input values, the corresponding output values must be different. Okay. So again, the x values, you can only use one type of x value and one type of y value. So the alternate definition, so here it is. This I'm sure is just reiterating. A function f is one-to-one if for any two range values f of u and f of v. Okay, so f of u and f of v, that it is the function at u and the function at v, right? And so it doesn't really matter what u and v are. And again, we can just say, you know, 3 and 300. Okay, if f of u is equal to f of v, so if f of 3 is equal to f of 300, well, actually that's not a good example at all. Okay. Well, actually, I mean it's not terrible because the implication would be that u is equal to v, and of course u is not equal to v there. So obviously my idea here is incorrect, but the definition isn't terrible. But I think the definition up here is actually better. Or again, the cornbread language one x, one y, period. Right? You can concern yourself with a's, b's, u's, v's all you want, but just know that if one x is going to a y that's already being used, it's not a one-to-one function. So let's go ahead and give a quick example. Actually, I know we're probably gonna do this example. More than likely, but for instance, let's look at this. Okay, this is the square function, right? X squared. Well, this is not a one-to-one function because, you know, like right here x equals 2, and here as x equals negative 2, we have the value here at 4, right? Negative 2 squared is 4, and 2 squared is 4. Well, we're using 4 twice, so that's not a one-to-one function. Okay, so the square function would not be a one-to-one function. However, what about the cube function? Okay, well the cube function is going to be one-to-one, right? Because for every one x value that I use, doesn't matter which, I'm only going to be getting one y value out. Okay, so the cube function is one-to-one function. And of course, we're going to, like I said, probably do a lot better examples than the ones I try to come up with off the top of my head. I really should publish a textbook, huh? My word, that would be awful. Okay, this might break things down a little bit easier. Maybe I should just go to the next page before I start freewheeling and thinking that I can explain things better, because this is actually really good. All right, so we see these two functions here. All right, this reads that figure 25a is 1-to-1 because for any two distinct x values in the domain, okay, so any two distinct x values, so any two of these on the x-axis here, and of course they're not being equal to each other, the function values of the range are not equal. And of course, like I said, I mean, this is a cube function, so that's what I left off with on the previous slide. Okay. B, figure 25b, we see that it is not 1-to-1 because we can easily find two different domain values that correspond to the same range. So notice how, again, these a's and b's, it doesn't really matter what they are, but just for the sake of this, let's go ahead and say that this is -1 and this is 1. Okay. Well, f of -1, we are up here at this point right here. Okay. And again, it doesn't matter. We can just call that 2. Okay. Well, f of 1 over here, well, that's also equal to 2. Okay, so that's why this is not a 1-to-1 function. Hopefully, I covered that right. All right, so luckily for you, there is a nice handy-dandy little test you can run, and it's called the horizontal line test. Okay, so the vertical line test helps you determine if a function is, if an equation is a function. Okay. A horizontal line test will help you determine if a function is 1-to-1. So easy enough, right? I mean, I'm just going to go ahead and snip this solution as well because it's pretty clear. All right, so again, we reiterate our horizontal line test there. So A, we run that horizontal line test, boom, boom. We see that, oh, we have C and D, so okay, maybe not. Maybe I shouldn't have pulled the solutions exactly. We'll still go over them, and I might need to scoot that over so I can. Okay, all right, so again, back to A. We run that horizontal line test. We see that we do indeed cross this graph in more than one area, so therefore A is not 1-to-1. All right. B, well, I mean, we can't cross it anywhere more than once anywhere, so therefore B is 1-to-1. Okay. So let's see, we'll just do, yes, oops, wrong one. We'll do B is, A is not. All right, now C. All right, so this is going to be a little tricky, and of course this is also going to be where being able to visualize these graphs in your head really help. But I'm going to go ahead and draw these because D you're going to have to. I mean, it's kind of hard for me to visualize that, so I'm assuming it might be hard for you too as well. All right, so C is f of x is equal to x squared plus 1. Okay. Well, now x squared plus 1, we know that as we know it's a parabola. Okay. And we know that it is plus 1, so therefore we're moving up 1 on the y-axis, right? So because we're adding 1 to the to the function, therefore we move up 1 on the y-axis. That is my vertical shift. Okay, so let's go ahead and just graph that just for the sake of it, right? So we do this, and right away we know that, okay, well, I mean, we can go ahead and say, nope, this is definitely not a 1-to-1 function because, well, it's a parabola, right? It is a square function. But look at the domain there, okay? So the domain is saying that we will only use the x values that are less than or equal to 0. Okay, so all the x values that are less than or equal to 0, okay, this is now my new graph. Okay, well now is this a 1-to-1 function? All right, well it looks like one, right? Because I mean nowhere do I violate my horizontal line test, and so therefore we would say that C is indeed a 1-to-1 function. And then D apparently is not, because like I said, I snipped this guy a little too fast on me. But let's go ahead and examine why D is not. And let me see if okay, so it just has an animation, so I am tasked with drawing this. That's fine. That's what I get paid the big bucks for. Okay, so for the sake of this, let's go ahead and denote this top one as blue and the bottom one is yellow. Okay. Alrighty, so the blue one is 2x plus 4. Alright, so we know that as, we're going to do this. Okay. Alright, so 2x plus 4. We need to go up 4 units on the x-axis, so 1, 2, 3, 4, and then it has a slope of 2. So it's going to be, so again, we are up here right now, and then we have a slope of 2, so it's a rise over run, so we're going to rise 2 and run 1. So we're going to start here, we're going to go up 2 and over 1, and so it looks something like this. This is going to be awful. Okay, so it looks something like that, but it's only for, looking at the domain, for only the x values that are less than or equal to a negative 1. Okay, so I'm going to have to erase everything that is above 1. Okay, and it's a less than or equal to, so this means that I can put a, did I say 1? I meant to say negative 1. So I can put a closed, dadgummit, this ain't working. There we go. Okay, good. Whew, okay, so that's that. Next up, we're going to do the other one. So we go down 6 on the y-axis. So 1, 2, 3, 4, 5, 6. So we're right here. And it also has a slope of 2. So we're going to go up 2, 1, 2, and over 1. And we're going to connect these dots. Oh my goodness. Okay. And this only exists for value. Oh no. Okay, so my graph looks horrible. Okay. But I guess we'll try to do this. But I can tell right now I did it not very beautiful at all. And it's, for x greater than or equal to 4. So we go up here. Maybe no, this ain't good. Okay. If one were to draw that graph correctly, it would indeed. Let's see. I haven't actually clicked on one of these before. Ooh, this one. All right. So, is this cheating? Is this cheating as being a mathematics instructor? Anyways, if I were to have graphed that perfectly, you can see that we will indeed violate that horizontal line test, and well, therefore it is not a one-to-one function. If that's cheating, I'm sorry. I don't know. That's all I got. I got nothing else to say. All right. So next up, we're going to talk about inverse functions. Okay. So inverse functions. Now they're a little bit harder of a concept because, well, now we have these funny little lines above my function. So let's go ahead and do this. Put a new page. Okay. So now we have these funny little things right here. Okay. Now, prior to this lecture, I mean, you're probably familiar with, or you've heard of inverse functions before, but prior to this lecture, you are familiar with the fact that if we raise an exponent to a negative, a variable to a negative exponent, then all that does is just basically flip the fraction there, right? Or change the sign and then flip the orientation. Well, inverse function uses that exact same notation, but it's different. Okay, so an inverse function is different from a negative exponent. Okay, as of right now, you need to go ahead and purge the thought of saying, oh, f of negative 1 is just basically 1 over the function. Okay, that is not true. You're going to mess everything up if you think that. Okay. Yes, the notation is being recycled. No, the notation does not mean the same thing. Okay. So what does it mean? All right. So wrap your heads around this one. If we let f be a one-to-one function, okay. So let's go back to my first page here. Okay. I said a function is an equation. I said a one-to-one function is a function which is an equation, and I said an inverse function is a one-to-one function which is a function which is an equation. Okay. So in order for a function to be to have an inverse function, it must be a one-to-one function. Okay. Only one-to-one functions can have inverse functions. All right. So this says, let f be one-to-one. Again, only one-to-one functions can be inverse functions. Okay, so f is a one-to-one function, has a domain of A and a range of B. Okay, so let's actually put this to the side because this is pretty important here. Okay, so we'll say f. Let's see, how did I do this before? Oh, that's what I did. Okay, so trying to remember how I put this in my other lectures. So I did f and f inverse. Okay. All right. So we're going to have the domain and range. The domain and range. Okay. This is super duper easy. Please don't tune me out just yet. Okay. So in my definition, f is a one-to-one function, has domain of A and a range of B. Easy peasy. So it has a domain of A and a range of B. Perfect. Okay. All right, and then continuing on, then f inverse is the inverse function of f. That's pretty easy, right? I mean, it's literally called f inverse, so therefore it's the inverse function of f. All right, it has a domain of B, okay, so domain of B, and a range of A. Range of A. Okay. So before we tackle the last sentence there, let's look at this. Okay. Notice how the domain of f is the range of A, is the range of f inverse, and the range of f is the domain of f inverse. Okay. So that's really it. Just notice that. You're going to be using that sometimes in your homework, and honestly, I think maybe on your final too. Okay. So yeah, they swap. All right, now let's tackle that last sentence. It reads, furthermore, if f of A is equal to B, okay, if f of A is equal to B, all right, well then the f inverse of B is equal to A. So notice how we just basically flip it, right? So I mean, if you want to think of this as, well, let's see, let's do it like this. I'm pretty sure this is how my brain made sense of this when I was going over it. Okay. Basically what happens is my function here, I'm going to move it from, actually let's do it this way. Okay. So what I'm going to do is I'm going to move the f from the left side to the right side, and then I'm just going to put that little negative exponent on there. And that's it, right? That's how the inverse function behaves, right? If I plug A into f and I get B, then for the inverse function, if I plug in B, then I'll get A. Right? And again, I know this is, it takes a moment to wrap your mind around, all right? But you just kind of have to read it, and then read it again, and then read it again, and then probably do a couple of examples to really fully grasp this concept, okay? And again, this is more concept-driven than computation, which again, in my humble opinion, is a lot more exciting. I much prefer concept-driven material than just mindless computation, as I've mentioned multiple times before. Okay. So next up, oh yeah, this is something that I definitely want to put here. How do we do this? Okay, here's what we're going to do. Alright, let's put stars here, and I'll circle it. I'll put an arrow here. Just for the sake of it, let's go and put some more stars here. Right here, right here. What else? What else should I put on here? Maybe let's put a sad face. Maybe an angry face. Is that an angry face? I don't know. How the heck do you draw an angry face? I don't know, but we'll stick it at sad because you have to memorize that. Okay, so yeah, it's very important. Right, I took longer than I probably should have to really kind of point that out. It is not the exact same thing. It is not the same thing as a negative exponent. Don't do it. You're going to miss everything. Okay. Hopefully I drove that point home. Alrighty, so here's a nice mouthful. Here, decomposition cancellation equations. Be honest with you, I'm pretty sure I say this literally, well, I guess maybe 2 times a semester or 2 times a year whenever I teach this class. But whenever I do inverse functions, you know, not gonna say my spare time, but like, you know, I do things sometimes. I never just say composition cancellation equations in my head. All right, but what is a composition cancellation equation? Let's start at the top because I guess, you know, again, the author wants to start here instead of down here first, so we'll start up here because there's probably a reason for it. The function f takes the number 2 to 8, whereas f inverse takes 8 back to 2. Observe what happens if we look at the composition of f and f inverse and the composition of f inverse and f at specific values, or specified values, sorry. All right, so we talked about composition functions last week. All right, when we take a function of a function. That's all we're essentially doing here is we're taking a function of a function, okay? Except this time the function of a function is an inverse function. We're going to be taking, and this right here, you see it, is f of f inverse. Okay, we're taking the function of the inverse function, okay, which, you know, notational looks like this, and therefore we get f of 2 is equal to 8. Okay, and then down here we see, you know, we take the f inverse of f. Okay, so again, that's the composition, and then of course we take, you know, the notation there, and then f inverse of 8 of 2, or I'm sorry, f inverse of 8 is equal to 2. Okay, so here, because of the undoing nature of inverse functions, we get the following composition cancellation equations. So as we said at the very beginning, these inverse functions, they undo each other. Well, we can use that thought process to formulate decomposition cancellation equations. Okay, so what this says is if we take f of f inverse of x, and we get x, okay, that's criteria 1. I guess criterion. No, let's do criteria here. So that's criteria 1. For all x in the domain of f inverse and f inverse of f of x, and we get x, that's criteria 2. For all x in the domain. Okay, so it doesn't actually say it. Well, if these two criteria are satisfied, then the two functions are indeed inverses of one another, and we'll see that on the next slide, I'm sure. So we'll put this to the test. Now, yes, okay, good. Okay, so go ahead and snip this up here so I can read it. Okay. So at the very top it reads, these cancellation equations can be used to show if two functions are inverses of each other. We can see from our examples that if f of x is equal to x cubed and f inverse of x is equal to the cube root of x, okay, we take the composition of these functions. F of f inverse, okay, is going to be f of the cube root of x. We plug that into x cubed, we get x out. Okay, and f inverse of f of x. All right, we plug in f of x, which is x cubed. We plugged x cubed into the cube root of x, which is the inverse function. We get x. Okay, since in both cases we got x, then they are indeed inverse functions of one another. Okay, so let's do us an example here. All right. So what I'm going to do first, I'm going to go ahead and do f of f inverse of x. Okay, and we know that was going to be, all right. So we're going to be plugging f inverse of x. Oh, okay, it's not. Okay, so they're g, so they're not. You have to verify their inverse functions. So sorry about that. We're just going to do f of g of x. Okay. So we're going to start first by going, we're going to be plugging g of x. We're plugging g of x into f of x everywhere where you see x. Okay, so let's go ahead and do that. So I'm just going to get, oh my goodness, this is going to be ridiculous really fast. Okay, so we've got 3x. That is actually the smallest 3 I think I've ever written in this course with this pen and tablet. All right, so it's that all over 2 times 3x over 1 minus 2x plus 3. All right, so this is awful. All right. So what I need to do here is I need to get a fraction on the denominator, just a singular fraction. That way I have a fraction over a fraction, which nobody likes, but we have to do anyways. Okay. All right, so this becomes over, and then we're going to have a 6x over 1 minus 2x plus 3. Okay. Now, like I said, we have to get a single fraction in my denominator, and let's just go ahead and snip this to the next page, because I feel like it's going to be pretty messy pretty fast. I'm running out of space. Okay, so in order to get that single fraction in the denominator, I need to multiply this 3 by 1 minus 2x over 1 minus 2x, right? So once I do that, I can get a common denominator and combine my denominators in my denominator. All right, and people wonder why so many people hate math. Might be this problem right here. All right, so we've got 6x 1 minus 2x, and then I said I'm multiplying this. I probably should have just kept it there. 1 minus 2x. I'm going to keep it there for right now. Okay, just so I can think my way through this. And again, I'm multiplying that by the 3 here. So I distribute the 3 through, so I'm going to have a 3. So it's going to be so we got a 3, and then minus 6x all over 1 minus 2x. Yeah, 1 minus 2x. Okay. Now I got that common denominator in my denominator, so let's go ahead and rewrite my numerator. Okay, my denominator now becomes, looks like 6x plus 3 minus 6x all over 1 minus 2x. Okay. Now this looks like a bundle of not fun. And the thing is, I mean, I'm not even going to lie, it really isn't. But we also know we can think of this as, let's do a different color. Start down here. We could think of this as 3x minus 1. Oh, I'm sorry. 3x over 1 minus 2x divided by 6x. And realistically, I mean, the 6's cancel, right? 6x plus 3 minus 6x. So I'm just going to go ahead and cancel those 6x's. And so it'll be 3 over 1 minus 2x, which we know is going to be, we multiply by the reciprocal, right? So times 1 minus 2x over 3. Okay? And when I have 1 minus, when I multiply by the reciprocal, I see that the 1 minus 2x's cancel, and the 3's cancel, and what remains is x. Whew. So that is f of x. Okay. So I'm sorry, that is f of g. So f of g is indeed equal to x. Again, that satisfies the first criteria. Now we got to go to the second one. No. I'm just going to go ahead and snip it from the next page. Okay, so that was f of g. Next up, we're going to do g of f. Okay, so g of f, hopefully it's a little bit easier. So g of f, again, of x. Okay, what I'm going to do is I'm going to plug in f of x everywhere where I see an x and g of x. And I can tell right now, I'm not going to like it, but yeah, this is the way it is, right? So we've got 3, and then x over 2x plus 3 all over 1 minus 2 times 2x plus 3 all under x. Okay. All right, so, oh gosh, this is ridiculous. In the numerator, I distribute that 3, so I'm going to have a 3x over 2x plus 3 all over 1, and I'm going to distribute the 2, so I'm going to have it 1 minus 2x over 2x plus 3. All right, so same thing as before. So on the previous page, what I had to do is I had to multiply this 3 by 1 minus 2x over 1 minus 2x in order to get that common denominator of 1 minus 2x. Well, something I didn't say, and I probably should have, is I'm allowed to multiply this 3 by whatever I want to, as long as it's a 1. Right? I could have multiplied it by smiley face over smiley face. That's perfectly fine, because smiley face over smiley face is equal to 1. Okay? So I didn't change the value of the 3 at all. I just changed the way it looked. Okay? So mathematically, there is little difference between this and this. I don't even know if that's ever a true statement. Let me try and think. I mean, it is 3, right? So I mean, I guess mathematically, yeah, it's the same thing, right? I just rewrote it and made it look different, okay? So that's what I'm going to do on this one right here as well. I'm going to go ahead and this is actually a lot easier though, because what do I need to multiply 1 by to get a denominator of 2x plus 3? Okay, well, it's just going to be 2x plus 3 over 2x plus 3, right? So same as before, let's go ahead and change the color. So we got my numerator here. Then my denominator, I've got 2x plus 3 over 2x plus 3 minus 2x over 2x plus 3. My numerator becomes 3x over 2x plus 3. And then my denominator, and same as before, it looks like I can go ahead and cancel my 2x's, right? This is 2x. Let's do a different color. This is 2x plus 3 minus 2x. So the 2x's cancel. So we're going to end up with a 3 in the numerator over 2x plus 3. And we know this is, and I'm just going to go ahead and, well, let's do this. I'll write it with the division sign. And then I'll just go change it to multiplication, right? Divided by 3 over 2x plus 3, right? So what I can do is I can change this division sign to multiplication and flip this fraction, right? So this becomes times 2x plus 3 over 3, and same as before, boom, 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 and we end up with x. Whew. Okay, so because I did f of g and I got x, and because I did g of f and I got x, I have now verified that these two functions are indeed inverse functions of one another. Okay. Now, if you thought that was horrible, you are correct, and you might be hoping, golly, there's got to be a better way. I think there is. Okay, I think there is. You got to bear with me, but I think there is. And matter of fact, it'd probably be what I would do, especially since because of COVID, I can't really check your work. I can't really see you verifying functions and inverses one another. So at the end of the lecture, we're going to figure out inverse functions, and then therefore we can we'll probably find a better way to do this example. Okay. Hopefully, I think it's better. Okay. So let me move this up here. Let me know if you watch the YouTube video, you can even see what I just did. I don't watch my YouTube videos. Okay, we're gonna go ahead and snip this as well, because I'm not even gonna play around and draw the graph myself. And I think, yes, okay. All right, here we go. All right, so this reads at the very top, sketching the graph of inverse functions, okay? So sketching inverse functions is pretty darn easy, right? As long as you can reflect about, something, you can figure out what the inverse function looks like. Okay, so let's go ahead and think about what that one thing is, right? So let's start here with this function. I'm sorry, this figure. Okay, so this figure, we have y is equal to f of x. Okay, f of x is just this line right here. Okay, if you are tasked, and you will be, with drawing the inverse function, well, all you have to do is imagine this line right here. That's the line y is equal to x, or the identity function that we have went over before. Okay, it's just a nice little slanted line right here. All you have to do is just mirror the inverse function across that line. Okay, and that's it, 100%. So if f of x is this x cubed, okay, so we know x cubed, right? Drawing red next to red probably isn't a good idea. Well, all you got to do is just mirror it across that line, and you have the inverse function. Okay, so this example reads, sketch the graph of f of x equal to x squared plus 1, where x is less than or equal to 0. Now, darn, I guess I should have done this one. Okay, well, we'll still talk about it. Okay, so bring your attention down here. Okay, read the top. Reads, sketch the graph of f of x equal to x squared plus 1. Well, this is where being able to visualize our functions really comes into play. Okay, so if we're to sketch the graph of x squared plus 1, well, we know x squared is this parabola, okay? Plus 1 tells me I'm shifting it up 1 unit on the y-axis, okay? And then the domain is the important part because it is for x values less than or equal to 0, okay? So we know right away that this function in a vacuum, all by its lonesome, is not 1-to-1, right? Because, I'm sorry, is not, yeah, I guess it's not 1-to-1. We know that it does not have an inverse function because it is not 1-to-1, sorry. But when we restrict the domain for the x values less than or equal to 0, that's when we get, now let's do this, like this. Well, let's do this. A little bit of art right here. We know that's what it looks like, but then when we restrict that domain, it looks like this. Okay, and of course we see a better drawing of that right there. Okay, and it wants us to sketch the graph of the inverse function. Well, all we have to do is look at this line right here, the identity function, and just basically mirror it across the way. Okay, that's it. Now, something I didn't talk about here. This reads, also state the domain and range of f and f inverse. Okay, well, realistically, you could probably look at this and tell. All right, but sometimes you can't. All right, it'll be easier to do things algebraically, okay? And this is just giving an idea of what it's like to do it algebraically. Again, this is pretty easy, but algebraically, the domain of f. Okay, what is the domain of f? Well, we know it's from negative infinity to 0, right? Because we look at this, and it's going from negative infinity all the way here to 0, right? Because again, that's where the domain is, first of all. But just looking at the graph, we can see that it is all the numbers, all the way to negative infinity. Okay, and we also know that the range looks like it's from 1 all the way to positive infinity. Okay, and so we get 1 to positive infinity. Well, figuring out the domain and range of the inverse function is as easy as what I showed earlier. All you have to do is just flip them, right? The domain of the f inverse is going to be the range of f, and then the range of f inverse is going to be the domain of f. And that's it, right? They just crisscross. And I'm pretty sure we do an example where we have to figure things out in this section. Let me see. Function. I'm wasting time. Oh, actually, we don't. Okay, I guess we don't do it in this section. We'll do it in the next section. Okay, it says find the inverse function that we discussed in section, or example 3. Oh, it's this one. Okay. Yeah, that's fine. All right, anyway, before we get ahead of ourselves, let's go ahead and jump to example 4. Okay, so does this even give us a step-by-step? Oh yeah, there it is down there. Okay, so anyways, let's see. Do I even follow that? We do that. Okay, so I do it tad differently, I think. No, it must be a pre-calculus class. Okay, so I actually do it exactly the same as this. Okay, so here we go. Step 1. Okay, so what we're doing is we're tasked to find the inverse function. So remember how earlier we did this monstrosity right here, right? I mean, nobody liked doing this, okay? And I said, I think there'll be a better way to do this, especially now that I can't verify, or I can't see that you verify that they are inverse functions. Instead, what we're going to do is we're going to find the inverse function. So we'll go back to that example as well, but we'll work on this one. So step 1, what we have to do is we're going to change f of x to y. Okay, so we change f of x to y. So now we have y is equal to 2x over 1 minus 5x. Okay. Step 2, we're going to interchange. That's, oh, Sherman, stop it. Interchange. We're going to interchange x and y. Okay, so interchange it. So we're basically just going to swap them. We have x over here is equal to 2y over 1 minus 5y. Okay. And then step 3, we're going to put on the next page. We're going to solve for y. Okay, so let's snip this and put this on the next page. No, darn it. Okay, so we're gonna have to, okay. Let's see, let's delete this page. Okay, so what was it? It was 2y over 1 minus 5y. Okay, so we need to solve for y. So in order to solve for y, I need to get the y's on one side. Hey, we're in luck. The y's are the y's are on one side. Okay, but we have one little problem. We can't necessarily solve this for y, can we? All right. So what we're gonna have to do is we need to isolate the y. See, I mean, we have the y's on one side, but we need to isolate the y. All right. Now this is where a little bit of manipulation and algebra comes into play. And by the way, pay close attention because you're gonna have a couple problems like this. I know that, and it's just the way it is. Okay. So what we're going to do is we're going to multiply both sides by 1 minus 5y. Okay, so by multiplying both sides by 1 minus 5y, I'm going to have x and then 1 minus 5y. That's going to be equal to 2y. Oh, not that. Sorry. It's just going to be equal to 2y. Okay, because I multiplied 1 minus 5y by 5y on each side. All right, they canceled out. Okay. So I multiply 1 minus 5 on either side. And next up what I'm going to do is I'm going to put the arrow down here because, you know, the continuation, I guess. We're going to go ahead and distribute the x through. Okay, so we're going to have x minus 5x. Oh, Sherman, why you do that? Oh, no. Wait, no, we'll do that. We'll do that. Okay. So we got x minus 5xy is equal to 2y. Okay. Well, now we have the y's on either side now. So how do we isolate the y's? Okay. Well, we have to do some algebra. Okay. So what we're going to do here is we're going to go ahead and we're going to add 5xy to both sides. Okay. So we're going to have x is equal to 2y and then plus 5xy. All right, this is where a little bit of cleverness comes into play. What we're going to do now is notice how in both these terms we have a y. Okay, so what can we do here? Well, we're going to take a step back all the way to the first couple weeks of this course, and we're going to factor a y out. Okay, so by factoring a y out, x is equal to, we have a y, and then we've got 2 plus 5x. Okay. And then we're going to divide both sides with 2 plus 5x. So we've got x over 2 plus 5x is equal to y. Okay, so we have now officially solved for y. Y is all by itself, and we solved for it. And then the next page, maybe I should, let's snip this, put on the next page first. And then square this. There we go. And then the fourth step, it is 4, right? Oh no, did I do the page thing again? I'm having a rough go, aren't I? Okay, so anyways, step 4, we're going to change y to f inverse of x. Okay, so we're going to change that. So we're going to have f inverse of x is equal to x over 2 plus 5x. Okay, and that's it. We have officially found the inverse function. Okay, using these 4 steps. Right now, earlier we was this is actually decent. Well, nah. Yeah, okay. We'll talk about it real quick. All right, before I do get carried away, it reads state the domain and range of f and f inverse. Okay. Well, the thing is, excuse me. The thing is, it might be a little hard to I mean, you can obviously graph this, you know, but at the same time, I mean, graphing this in your head, yeah, we didn't really prepare for that, did we? No. You can graph it on a calculator, or you could do it this way. Okay, so we're going to write f, and we're going to write f inverse, just like this. Okay, the domain, and the range, the domain, and the range. Okay, well, we know how to find the domains pretty easily, right? Well, let's just look at f of x. All right, well, what is the domain? Okay, well, the domain is going to be every single number except for what makes this denominator equal to 0. Okay, well, what makes that denominator equal to 0? Well, it looks like it'd be 1/5, right? 5 times a fifth is equal to 1, and 1 minus 1 is 0. Of course, you can always, let us do this anyways, 1 minus 5x equal to 0. You do that. You add 5x to both sides, so you got 1 is equal to 5x, and then divide both sides by 5, and you get 1/5 is equal to x. Okay, so that's how you know that 1/5 is not in the domain. So we would say probably a little close there. All right, so shoot. Okay, I'm going to put. No, I like the format that I'm trying to do, so I'm going to put it over here. Okay, let's little divider there. Okay, so the domain is every number except for 1/5. So that's a 1/5 unioned with 1/5 to infinity. Okay, so that's the domain of f. Well, what's the range of f? I don't know. Okay, so I'm just going to leave it alone. So next we're going to look at the domain of f inverse. Okay, what's the domain of f inverse? Well, this is f inverse. Okay, so what I have to do again, just if I set this equal to 0, well, yeah, I guess that, now let's do it this way. 5x equal to negative 2, and x is equal to a negative 2/5. Okay, so negative 2/5, I can use every single number but negative 2/5 in f inverse. Okay, so every number but negative 2/5. So the domain of this is every number but negative 2/5, and I've done messed myself up, haven't I? Negative 2/5 unioned with, oh, dadgummit. Okay. Maybe. Oh, yeah, of course it is. Okay, this is nice and neat, and we're just going to go ahead and not put it there. We'll put it here. I wanted to try and show it, the thought process, and I guess I still can. All right. You know, the domain of f is every number but one. Ooh, that's what I can do. Okay. The domain of f is every number except for it cannot be equal to 1/5, and the domain of f inverse x cannot be equal to, what do we say? Negative 2/5. Okay. All right. So obviously this is an interval notation, and we'll see interval notation here in a moment. But I just want the thought process. The domain of f was all x values, but x cannot be equal to 1/5. Okay. I don't know the range because I can't tell a range with just looking at this, right? I can't tell a range doing this algebraically. Okay. Same thing with the domain of f inverse. I can't tell a range of it, but I can tell the domain. So all I have to do to find the range of f is, I know the range of f is just simply the domain of f inverse, and I know the range of f inverse is simply the domain of f. And this makes it look a lot better. Again, we did the domain and range of f, the domain and range of f inverse, and again, like as I mentioned before, they crisscross. Okay. Now, pretty sure. I've got plenty of time. Let me make sure. Yeah, I got plenty of time. What I'm going to do is I'm going to go back and I'm going to do that one example where I said this is ridiculous. There's got to be a better way. We're going to try that better way. Okay. So we're going to try that better way right here. Okay. We're going to find the inverse function of f of x. So f of x is equal to x over 2x plus 3. X over 2x plus 3. Okay. Yeah, I think that's right. Okay. So anyways, let's do this. So step 1, we change f of x to y. So we're going to just change it to y like this. Oh, let's put it in white. Be consistent. Okay. Step 2, we interchanged x and y. All right. Step 3, we solved for y. Okay, so we're going to solve for y. Looks like the same procedure as the last one, right? We're going to multiply both sides with 2x plus 3. So we're going to have x times 2x plus 3 is equal to, that's supposed to be y, times 2y plus 3 is equal to y. We're going to, again, distribute that x through, so we're going to have 2xy plus 3x is equal to y. We're going to go ahead and subtract, so subtract 2xy from both sides. So we're going to have 3x is equal to y minus 2xy. We're going to factor out a y, so we're going to have 3x is equal to y, and then 1 minus 2x. Excuse me. And then we're going to solve for y. We're going to isolate the y, right? So we're going to have y is equal to 3. Let's put a different color. We're kind of running here. Y is equal to 3x over 1 minus, I knew I was going to move that, dadgummit. Okay, well now I want to, there we go. 1 minus 2x. Okay, and then step 4, we'll just put up here, step 4 was change y into f inverse of x is equal to 3x over 1 minus 2x. Okay, so 3x over 1 minus 2x, boom, look at that, 3x over 1 minus 2x. So, I know that took a long time to get to this point, but, if you honestly, if you don't want to verify, by plugging in and do everything we did, on example 2, you could just simply go ahead and find the inverse function and be like, oh yeah, that's verified because I found the inverse function, there it is, therefore the inverse functions of one another. Obviously you can, if you want to, plug in the composite functions, but as you can tell, this looks a little bit easier, right? Alright, so let's get to the last example, and we'll be done. Okay, so this reads, find the inverse function, the inverse of the function that we discussed in example 3. So if you forgot, example 3 was this, and the inverse function that we got was this red line down here. Okay, so we're going to try and find the inverse function, or we're going to try and find out what that function is algebraically, sorry. Okay, so in order to find out what that function is algebraically, we're going to have to do what we just did. Okay, that 4-step process. Okay, so step 1. Right, which by the way, this domain is going to come into play, right? And we're going to see why here in a moment. Okay, so we're going to go ahead and change. Step 1 reads change f of x to y. So there's that. Step 2, we interchange x and y. So we're going to have an x equal to y squared plus 1. Step 3, luckily this is just a nice sigh of relief here. It's going to be pretty easy to solve for y, right? We're going to let's go and put the y squared on the left side. Let's go ahead and we're going to subtract 1, so we're going to have x minus 1, and so we've got y is equal to plus or minus the square root of x minus 1. Okay. So, excuse me, because the domain, like I said, is going to come into play, okay, my value here is x is less than or equal to 0, okay? So this means that the domain of f, right, my original function, the domain of that is all the values that are less than 0, right? And of course we saw that here, okay? The domain is indeed all the values that are less than 0, okay? So what that means is that the range must be from -infinity to 0. The range of this function. Sorry, the inverse. Yeah. Oh yeah. No. Oh, I didn't actually do step 4. That's why. Okay, so let's actually do step 4 because I was looking for the notation. So the notation here is f inverse of x. Should have done that first. Sorry. Okay, so let's try this again. So if the domain, let's start it all over, dadgummit. Right here. The domain of my original function was from -infinity to 0. Okay, that means that the range of my f inverse, of course we see that here, is from -infinity to 0 as well, right? Because we crisscross. Okay. Excuse me. All right. So since the range of f inverse is from -infinity to 0, okay, that means that we're going to be using the negative sign. Okay, so let's let's try this one more time because it takes a minute. So I got this as my solution. Okay. Well, I can't have two of these functions, right? Can't have a plus the square root and a minus the square root, right? The plus square root, you know, looks like, well, the positive square root looks like this, right? And then the negative of the square root, right? Negative of the function, we know looks like it mirrors across the x-axis, okay? So we're not using the positive component because we have to think about the domain and ranges here. Okay, since the domain of f was negative infinity to 0, and that means that the range being, you know, where we appear on the x-axis, is going to be negative infinity to 0. Okay, the range being, you know, so, gosh, let's see. Here, let's try it. Obviously, this is, you know, I wouldn't say cheating, but we know that this is the domain of f. I just don't feel like I'm explaining it right. That's why I keep going over it. That's the domain of f. We see that here. Okay. Well, since that's the domain of f, then we know that that is the range of the inverse function. And the range corresponds with the y-axis, right? Corresponds with the y-axis. All right. Well, the only other the other option, the positive component of this particular function would look like this, right? Because, you know, if we take the negative of the function, we mirror it across the x-axis. So the positive component, you know, the y plus or minus that, looks like this blue line here. Well, we know it cannot be that blue line because the range is from negative infinity to 0. Okay, and this is the negative infinity to 0. So therefore, we know that we're not going to be looking at the positive component there. So therefore, that is my that is the inverse function. Okay. Whew, hopefully that wasn't too bad. I do know that oh, look at there, they actually give it again. I knew that because I actually clicked on this earlier. But anyways, that does conclude today's lecture. Let's go ahead and do this. The summary. Okay, that does conclude